For the dimmers, there's not a ton of information we have to talk about. I think the biggest thing is, what can be controlled by a dimmer or what should be. And I think it's easier to maybe say what shouldn't be. So a big one is fans, ceiling fans, exhaust fans. Another one that you can't control, a plug load or receptacle load with a dimmer. Simple fact is we don't know what anybody's going to plug in to that receptacle. So we should only be, dimmer controlling light fixtures, hardwired equipment that we know for a fact is dimmable. So essentially, your light fixtures, but no fans, no plug load. That's some big ones there. Next up, let's hit the closed closet lighting. Sounds like a specific thing, and frankly it is. But the code has a specific section here, 410.16, luminaires in closed closets. Right here is essentially your answer to any test question you're going to see on the exam. So what do we have here? Essentially, how close can our light fixtures be to the storage space? Number one tells us 12 inches for surface-mounted incandescent or LED luminaires with completely enclosed light sources, 6 inches for surface-mounted fluorescent luminaires. So it sounds weird that what do they say here? An incandescent and an LED have to be 12 inches, but a fluorescent only has to be 6. Well, I thought LEDs were the coolest burning thing around. Well, they are. But in this case, they're kind of talking about a LED light bulb, an incandescent light bulb. We can't control what light bulb somebody would screw into a light fixture. This is a little bit outdated as a lot of fixtures now have integral LEDs, but nonetheless, that's the info that we have. Number 3, 6 inches for recessed incandescent or LED luminaires with a completely enclosed light source. Number 4, 6 inches for recessed fluorescent luminaires, whether they're enclosed or not. And then number 5, this is kind of the special one here, the newer one. Surface-mounted fluorescent or LED luminaires shall be permitted to be installed within the closed closet storage space where identified for this use. So they're making out basically LED fixtures that are listed for closed closet. So those, it's kind of like all bets are off. Do whatever they're listed for. Let's get into some conductor terminology. There's essentially 3 main conductor types you guys are responsible for. That's going to be your ungrounded, it's going to be your grounded, and it's going to be your grounding. Right? So what are each of these? What does that actually mean? So in layman's terms, your ungrounded is your hot conductor, right? Your grounded, ending in ED there, that's going to be generally known as your neutral conductor. Not always, but you'll get into that in year 2 in a little more detail. But 99.9% of the time, neutral, grounded, talking about the same thing. Grounding is your actual ground conductor, right? So I think the next thing to maybe drive these points home is what color can all these things be? Well, let's kind of work our way back up. Your ground can be green. It can be, you may see sometimes green with a yellow stripe. And it could also be bare. It doesn't need to be insulated. It can be bare copper, bare aluminum. For your neutral, pretty simple, white or gray. The reason they have 2 colors, if we had 2 different voltage systems within the same building, which we quite often do, a 120/208, a 277/480, we've got to differentiate the neutrals for each system. That's why we have 2 different colors. And then essentially for your hot conductor up here, it's anything else that we didn't mention below, right? Any color goes. Next one here, I want to talk about the voltmeter reading subset of questions. I think we saw some of these on the midterm. These can be tricky, but this is the type of question where they say, if I place my voltmeter lead here and here, what do I expect my voltmeter to read? And I think the way to think about these is here, first of all, we have to recognize these are connected in series. Think back to that series circuit problem we just solved for. In this case, I believe they tell us these 2 elements are equally rated. So here's element 1 is this little piece. And then element 2 is going to be this little piece. Okay, they're equally rated. So what do we know about equally rated loads? We hook them up to a 2-pole 240 breaker right here. Each one of them has to consume an equal voltage. E1 plus E2 has the equal E total. So again, 240. I have 2 loads. Each one is going to be half of that in this case. Each one gets 120 volts. So if I place my voltmeter leads, here on the, that's way too big, on the breaker, first of all, I'll get a smaller pen size. If I place my voltmeter leads here on the breaker, what do I expect? Well, I'm right at the source. I expect to see 240. So let's kind of walk this out. If I place my voltmeter leads on T1 and T4 now, let's say, what do I expect to read? Well, the question is, have I crossed any of these voltage consuming elements here? Have I dropped any volts by being on the other side of one of these elements? And I haven't. I'm still directly connected to the breaker with these two pieces of wire right here. So I'm still going to read 240, right? But now let's go ahead and move our voltmeter lead down to here, T3. So now let's read between T1 and T3. What do we expect in this case? Well, I've crossed over this element now. Or in other words, to get back to source, I would have to go through this element. This element drops or consumes or uses or has 120 volts applied to it. So basically I'm dropping 120 volts by crossing through this. So if I started with 240, I dropped 120, I'm going to have 120 left. That's what my voltmeter should read. If I kind of do the same, but we're looking at a mirror image almost here, if I put my voltmeter leads now, T2 and T4, same situation. They were just using the other element now. I've crossed over this element, or this element consumes 240 volts, or I'm sorry, consumes 120 volts. If I started with 240, I drop 120, I'm left with 120. So I would expect to read 120 in this situation. Last thing to look at, if I put my voltmeter leads here and here, how about? What do I get? There's two ways to look at this. Both are very correct. First one's a lot more technical, but essentially I started with 240. I've crossed this element, that drops 120. I've crossed that element, that drops 120. Of course, 240 minus 120 minus 120, I'm left with 0. But the other way to look at it, and I think the simpler way, maybe the more common sense way, when I measure voltage, that's the difference of electrical potential between 2 points, okay? What's the difference of potential between these 2 points? Well, it's none. They're effectively the same point electrically. I just have this little jumper of wire between them. There's no kind of load or anything. That's effectively like touching my 2 voltmeter leads to one another. That's going to be 0 all day long. There's no difference of potential at that point. So either way, that one is going to read 0. All right, so then next up, let's look at some receptacle types. So here we have an isolated ground receptacle. We know that based on this green triangle that we see right here. Whether this is an isolated ground receptacle or not, a few things are going to be true. This prong here is going to be for our hot. This one over here, the vertical piece is a little longer. In this case, it's a T shape, which indicates it's actually a 20 amp receptacle. But this is your neutral conductor. On a 15 amp receptacle, you'd only have this vertical part. But being a 20 amp receptacle, it's got this T shape. Then this one down here is going to be your ground. What's special about this isolated ground receptacle is we do not have any continuity from our ground terminals to this metal yoke strap or the body of the receptacle. It's a totally isolated ground, as the name implies. So, next up, let's kind of jump over to this table. I want to talk about the NEMA receptacle classifications. So there's essentially 4 parts to a NEMA, receptacle naming function. We're going to either have an L, or we're not going to have anything. Could be blank. So in this case, let's compare. Let's look at our L 520 compared to the 520, right? So L indicates locking. So L520 is a twist lock receptacle, or a locking receptacle, indicated by this L. Our next number is essentially a configuration type. I don't need you to memorize what the 5 is, what the 6 is. They all have significance. The 5 is, a hot, a neutral, and a ground, rated 120. Those combinations can be pretty unwieldy, but what you need to know is that first number. So we have the L or not, and then we have our first number. That's configuration type. Then we're going to have a dash. Then we're going to have our next number is always going to be amperage, right? So in this case, these are all 15s, 15. Now this guy here is a 20, right? You might have a 30, you might have a 60, but the number after the dash indicates your amperage. And then last but not least, and it's not shown here because it's not relevant, but you could have an R, you could have a C, or you could have a P. The R indicates receptacle. That's a device that you're going to, mount to the box in the wall. The P indicates it stands for plug. It's essentially a male cord end, a male plug. And then the C is going to be a cord or a cap or a female cord end to a plug. So essentially here again, what do we have? We have an L or not. You guys need to know that the L indicates locking or twist lock. 5 or any number here at this point, but that number before the dash indicates configuration type. The number after the dash is always going to be your amperage. And then again, you're going to see R, you're going to see P, or you're going to see C. Receptacle, plug, cord. Okay, then to round things up here, let's talk about GFIs a little bit. Honestly, I think the best way to do this is just to explore their operation. Once we get that in our heads, I think everything beyond that is a little bit easier to imagine. So again, you really want to try to get the understanding of how this thing functions here. So this hopefully looks familiar from the video we posted up on the site. But we're looking at the insides of a GFI. We've got hot conductor going out, it goes through our load, which is plugged in here, and then back through the neutral. And then we got a bunch of components here, right? So we have the shunt trip, which is going to essentially work in our, it is what's going to cause the GFI to open if there is a short. You guys don't necessarily need to know all these terms, but they're in the slide anyway. But we have a 12 amp load plugged into this GFI receptacle. So if we have normal circuit conditions, everything's fine. What happens? With or without GFCI protection doesn't matter because everything's normal. We have a 12 amp load. We have 12 amps going out through the hot. It goes back through the neutral. Where else would it go? Everything's normal. You can see if they put a little amp clamp there, you got 12 amps going through the ungrounded conductor. We have 12 amps going through the grounded conductor. Life is good. Nothing's going to trip. That situation will continue indefinitely till we turn it off. But now let's say if we have GFCI protection and we have a ground fault, right? So again, normal conditions, I have 12 amps going out, 12 amps going back. Here comes this sharp dressed guy. He somehow touches something he shouldn't and becomes a path to ground. That is a form of ground fault. Current going to ground at a place where it shouldn't, right? So now what happens? This guy his body has resistance, right? He has such high resistance that only 0.12 amps is going to go through him. They actually calculated in the textbook. Humans are actually really bad conductors, but also we can't handle much electricity, so it's kind of a good and bad there. But so this guy essentially now has 0.12 amps going through him, right? Now, it wouldn't go on for this long because thankfully this is a GFCI circuit, but what happens is we see 12 amps plus 0.12 amps going through our hot, or 12.12. We only see 12 amps going back through the neutral. This toroidal coil, as it's known, is what kind of monitors. Basically, a GFI wants to see a balance between hot and neutral current. We've just created an imbalance, more currents going out than what is returning. So only 0.12 flows through him, but it's an imbalance of 0.12. Ground and ungrounded conductor are not balanced. Our GFCI is going to trip, and it's going to open the circuit. So this guy's, can now let go of this thing. So, again, that's kind of a brief overview, but that's about as far as we get with GFCIs. There's not a ton of stuff. I think it's more important to kind of get the concept there. I think that kind of wraps you guys up. Gets you to where you need to be for your GFCIs. And again, I think that's a nice overview of all the topics we see there. So hopefully you guys found this pretty helpful.